Thermodynamic, temperature, and pressure. How do we define temperature and pressure as functions of the fundamental properties mass, volume, internal energy, and entropy? We have over here two masses, which we label A and B, which are initially at different temperatures, TA and TB. We bring them together and we insulate around them, and we let the two masses come to thermal equilibrium. Both of them will then be at the same temperature. We define system C as being the combined system A plus B. The question we want to answer is, what is the condition for equilibrium to be reached in system C? We can analyze this using our postulates. We'll use first the state postulate, which says that the entropy of A is a function of UA, VA, and MA. Similarly, the entropy of B is a function of UB, VB, and MB. Entropy is an extensive property, so therefore the entropy of system C, SC, is equal to SA plus SB. And the second law tells us that at equilibrium, the entropy is maximum, which means that DSC will be equal to 0. Now, systems A and B have constant volume and mass, so MA, VA, MB, VB are all fixed. The only variable which can change are UA and UB. So we write SC as being equal to SA plus SB, and then we differentiate that. So DSC will be the partial derivative di SA by di UA, holding MA and VA constant, times DUA, plus di SB by di UB, holding MB, VB constant, times TUB. And at equilibrium, this must equal 0. Now, in addition, we know that C is an isolated system, so its energy is constant. So therefore, UC, which is UA plus UB, is constant. If we differentiate this, we get that DUC, which is DUA plus DUB, must equal 0. Or DUA is equal to minus DUB. Now it's easy to understand what this means physically. It says that any energy change in A must show up as an energy change in B with an opposite sign. If the energy of A goes down, the energy of B must increase. Let us go back to our equilibrium condition for DSC. We have just shown that DUB is equal to minus DUA. Substituting this, we can say that DSC is equal to di SA by di UA minus di SB by di UB, the whole thing multiplied by DUA, and this must equal 0 at equilibrium. Now, the magnitude of DUA could have any arbitrary value. It would depend on the size of system A, on its temperature, and on its thermal properties. So therefore, in general, for this equation to be satisfied, the term in the brackets must equal 0. So for thermal equilibrium, we need that the partial derivative di SA by di UA must equal to di SB by di UB. So what does this condition mean? We know from our understanding of the word temperature that at equilibrium, TA must be equal to TB. From our analysis, we have also shown that these two partial derivatives must also equal each other at equilibrium. Now, in our development of thermodynamics, so far we have not given a definition of temperature. So we are going to now define a new property, temperature, T, and we are going to define that as being the partial derivative du by s holding m and v constant. Now to do this, we will have to show that this definition satisfies our usual understanding of the word temperature. So if we look at the equilibrium condition, then for these two partial derivatives, we can substitute 1 upon Ta and 1 upon Tb respectively. So therefore dsc would be 1 upon Ta minus 1 upon Tb times dua equal to 0. So since dua can have any arbitrary value, to satisfy this equation, we require that Ta is equal to Tb. And when this is satisfied, dsc is going to be equal to 0. So therefore, the system is at equilibrium. Now this satisfies our understanding of temperature, that when the temperatures of two systems are the same, they are at thermal equilibrium. But in addition, we have to see what happens if the temperatures are not the same. So let us assume that Ta is greater than Tb. In this case, the system is not in equilibrium, and therefore the entropy must increase. So dsc, which we have just said is 1 upon Ta minus 1 upon Tb times dua, must be greater than 0. Now if Ta is greater than Tb, this term in brackets would be negative. Therefore, to satisfy the inequality, dua must also be less than 0. dua being less than 0 means that the energy of system A decreases, while the energy of system B increases. Therefore, we've got heat transfer from A, which is the body at higher temperature, to B, which is at lower temperature. So our definition of temperature satisfies our understanding that at thermal equilibrium, the temperatures must be the same, and that heat transfer takes place from the higher temperature to the lower temperature. We now want to analyze the case of mechanical equilibrium. We have over here a cylinder which is separated into two compartments by a sliding piston. The piston is initially held in place by a locking pin. The two compartments, which you label A and B, initially have different pressures, Pa and Pb. The pin is removed, the piston slides until it reaches equilibrium, and then both system A and system B have the same pressure. If we call the composite system consisting of A and B system C, we again want to see what is the condition for equilibrium to be reached by system C. We can start with a state postulate, which says that SA is a function of UA, VA, and MA. SB is a function of UB, VB, and MB. Entropy is an extensive property, so SC is equal to SA plus SB. And the second law tells us that at equilibrium, the entropy is maximum, so DSC is equal to 0. Now in this case, systems A and B have constant mass, so MA and MB are fixed. But UA, UB, and the volumes VA and VB all can change. So now when we write DSC, we end up with four terms. We have a partial dSA by dUA times dUA plus dSA by dVA times dVA plus dSp by dUp times dUp plus dSp by dVb times dVb. C is an isolated system, so its energy and volume are constant. So UC is equal to UA plus UB is a constant. VC is equal to VA plus VB is equal to constant. So differentiating, as we just did, we can show that DUA is equal to minus DUP, DVA is equal to minus DVB. So any change in energy or volume of system A must show up as an equal and opposite change in system B. Going back to our expression for DSC, we know that the partial derivative dSA by dUA equals 1 upon TA, dSB by dUB equals 1 upon TB. So let us substitute those expressions. DSC must equal 0 at equilibrium. DUA can have any arbitrary value. Similarly, dVA can have any arbitrary value. So if the system is at equilibrium, we require that both these expressions in brackets must equal 0 independently, which means that TA is equal to TB. And these two partial derivatives, dSA by dVA, must equal to dSB by dVB. So what is the meaning of this equation? That dSA by dVA equals dSB by dVB. What does this condition mean? Now, before we go and start defining a new property, remember that all of these variables, S, V, M, U, they all have units. So what are the units of this partial derivative? S, the entropy, has units of joules per Kelvin. So the dimensions are energy divided by temperature. Energy has dimensions of force times length. The units of V, volume, are meter cube. So the dimensions would be length cube. So the dimensions of the partial derivative, dS by dV, are force times length divided by temperature times length cube. We can simplify that and write it as force divided by length square divided by temperature. And force per length square we know is equal to pressure. So the dimensions of dS by dV are those of pressure divided by temperature. So let us define P upon T as being equal to dS by dV holding M and U constant. Substituting this back into expression for DSC, we have that 1 upon TA minus 1 upon TB times DUA plus PA upon TA minus PB upon TB times dVA is equal to 0. So if the system is at equilibrium, we require that TA is equal to TB and that PA is equal to PB. And this satisfies our understanding of temperature and pressure. So let us analyze what happens when the pressures are not the same on both sides of the piston. So let us assume that the temperatures are the same on both sides. So TA is equal to TB, in which case we can drop the subscript and just call the temperature T. But let us assume that PA is greater than PB, in which case the system is not in equilibrium and the entropy will increase. In this case, DSC must be greater than 0. Now, if TA is equal to TB, that first expression is equal to 0. Taking T common, we have 1 upon T times PA minus PB times dVA is greater than 0. If PA is greater than PB, then PA minus PB must be greater than 0. The temperature is the absolute temperature, and therefore it must always be positive. So to satisfy the inequality, we need that dVA is greater than 0. This means that the system A expands, and remember this is the system at higher pressure, and B contracts, which is the system at lower pressure. And this also satisfies our understanding of pressure, that systems at higher pressure would expand and systems at lower pressure would contract. To summarize, temperature and pressure are not fundamental properties, but functions of mass, volume, internal energy, and entropy. The temperature is defined as the partial derivative du by ds holding m and v constant. Pressure is defined by the equation that P upon T is equal to ds by dV holding m and u constant.